dive into our first case study, Project Bina Baru Masjid Indra Sempurna in Kuantan, Pahang. To give you a quick overview of the project background shown on the slide, the site was handed over on 5 March 2025 with a project value of 9.31 million. The original timeline target completion by June 2026. The scope of this project is comprehensive. It covers everything from critical substructure and RC piling work to the main mosque facility such as the ablution area, a minaret and external reticulation work. Behind this project, we have 4 key parties involved. The client is Jabatan Agama Islam Negeri Pahang and the SO is Pengarah Kerja Raya Negeri Pahang, represented by JKR Daerah Kuantan, and the main contractor is Network Builder Sdn Bhd. Moving to next section of the slide, let's look at the design consideration for the foundation. First, due to the heavy and concentrated load from the dome, minaret and wide prayer hall, a deep foundation is required. The solution chosen here is RC square end bearing pipe measuring 200 x 200 meter with a working load capacity of 250 kN per pipe. These pipes are driven to a depth of about 24 meter to reach the stable, competent bearing soil layer to achieve this depth. Shorter pipe sections, specifically 12 meter joints, are welded together during the driving process. To conclude the foundation work safely, the engineering team applies the Hadley formula. This allows them to verify the final site and guarantee that each pipe meets the exit load capacity required before completing the foundation work.
Hi, my name is Shohada and I will explain about the site construction method justification for our first case study, which is the new mosque in Kuantan. For this project, we use precast reinforced concrete driven square piles, measuring 200 mm x 200 mm. Why was this method chosen? A mosque has concentrated structural load at specific heavy zone, like the minaret and main prayer hall. Precast piles are fabricated off-site in a factory, meaning they offer superior quality control and eliminate time needed for concrete to cure on site. To reach the required depth of roughly 24 meters, individual pie sections were joined together using butt welding at the joint. We also used mild steel pie shoes at the bottom tip to prevent the concrete from cracking when driven into hard soil layers.
My name is Natika Najwa. Let's begin with material use. Material selection is strictly driven by structural loads and ground condition. For the mosque project in Pahang, we utilize 200 mm x 200 mm precast reinforced concrete square parts. Cast in controlled factory setting, this achieves a high concrete strength of grade 45 or above, which is crucial to withstand intense dynamic driving stresses. To reach the required design depth, multiple segments were spliced on slide using mild steel joint plates and high penetration structural welding. In contrast, the FT003 infrastructure upgrade in Kelantan demanded 1,800 mm diameter cast-in board pile to support massive bridge piers and dynamic traffic loads over a soft river bank. Here, we use high slump, self-compacting, ready-mix concrete of grade 35 to 45 formulated with the tartars to delay setting during long pours. Heavy yield deformed steel reinforcement cage were fabricated on site and lowered into the shaft. To prevent the loose riverbank soil from collapse, thick permanent steel casing were installed near the surface, paired with a specialized bentonite slurry fluid to hydraulic stabilize the borehole walls. This brings us to equipment and machinery, which highlights the physical execution of displacement versus replacement methods. For the precast piles in Pahang, our primary machine was hydraulic hammer rig. Hydraulic hammer offer excellent efficiency because operators can precisely control the drop height and the drop height and impact energy, minimizing pile head damage. An excavator was also retained on site to clear shallow timber obstruction and punch through hard upper soil crust. Conversely, the Kelantan project required high torque rotary drilling rigs equipped with telescopic calibers. Operators use soil augers for the upper clay layers, but once they hit competent sheet bedrock at a deep a depth of 70.3 meter. They switched to core barrel strip in tungsten cartridge teeth to execute rock socketing. After drilling, a service crane lowered the steel cage. A concrete was discharged via trainee pipe system. This system poured concrete from the bottom up, cleaning displacing the drilling fluids without mixing or segregations. Descending plant, filter, and recycle the bentonite slurry. My final subtopic is testing methods, which bridge theoretical design with real-world empirical validation. To detect structural defects like cracks or voids, non-destructive integrity tests are mandatory. We use PIT, pile integrity test, via the sonic echo method for the driven piles, and CSL, cross-hole sonic locking, via ultrasonic transducer from the port pile to fully map the internal concrete matrix. To verify load capacity, the gold standard in the statistic maintain load test (MLT), applying up to 200% of the design load using hydraulic checks and monitoring settlement over 25 to 48 hours. Because MLT is time-consuming, it is supplemented by high-strain dynamic load testing or PDA, where a heavy weight is dropped into the pile to capture force and velocity data, which is refined via CAPWAP computer software to isolate shaft friction and bearing values. Finally, for the real-time fluid validation during driving, we rely on mathematical verification of the Healy formula.
Next, let's talk about the effectiveness of this choice. The 200mm x 200mm sizing was highly effective because it perfectly matched the load demand of medium-scale building without unnecessary over-engineering. Structurally, this functions as an ending bearing pile system. This means the structural weight of the mass is transferred directly down through the pile into highly competent, hard bedrock stratum rather than relying on weak skin friction. This secure anchors the heavy roof and minarets, completely eliminate the risk of hazardous, uneven settlements over time. Regarding the financial aspect of case study 1, piling work make up a significant portion of the substructure budget. Because underground soil condition can be unpredictable, the piling item in the bill of quantity were classified under provisions quantities. This is a standard industry practice that means the final costs are based on actual site measurement after driving is complete. This financial approach protects the client from paying for unused material while ensuring the contractor is paid accurately for the exact depth driven.
Hi, my name is Nudini. So now I will present about the problem arising for this project. So the first issue for this project is the changes of pile from 6 meter size to 2 of 9 meter size and 1 6 meter size of piles. So the problem is when using a lot of piles of 6 meter, the workers had to wet the piles together 3 times, where more welding take more time because the workers need to align the piles and weld them. So every welded joint is a weaker point, which can make the pile has a higher chance of cracking or breaking. So to solve the problem, the pile arrangement was changed to 2 meter to 2 of 9 meter piles and 1 6 meter pile, which only needs 2 reds instead of 3, which can save time, reduces work, and makes piles stronger. So for future recommendation, the soil investigation report should be checked carefully before drilling the piles. If the ground is soft, longer starter piles should be used from the beginning. And for the second issue is pile hit a wooden construction at 1 meter depth. Because of this, the pile cannot go deeper. If the piling continue, the concrete pile could crack, break, or move to one side. So the piling was to stop immediately, which excavator was used to dig ground and remove the wood. After removing it, the hole has to fill with suitable material, suitable soil, and compacted properly. Then the piling can continue without any problem. For recommendation, the site should be checked before piling start. Trial pits can be dug to find and remove buried woods and roots. And for site with a high risk of underground obstruction, a pre-boring machine can also be used to drill through small obstacles before driving concrete piles.
Next, look at the case study 2 on the slide, which involved the road upgrading and intersection project at BE224 and FT196 Pasir Mas, Kelantan. The project scope here is quite technical as it involves specially bridge engineering. It starts with critical deck foundation work, specifically board pile. After that, the focus moves to the bridge substructure, such as the abutment and piers, and the superstructure using pre-stressed T-beam and deck slab. It also covers structural coordination mechanism and road upgrading work. Finally, for the project team, the client for this development is Jabatan Kerja Raya Malaysia, and the execution is handled by the main contractor, Arus Energy Sdn Bhd. Let's discuss the design consideration for the bridge foundation. First, due to weak upper soil condition, a board pile system was required. The design specified 1,800 mm diameter cast in place board pile, scattered 70.3 meter depth into the cheese bed road to achieve the required load capacity. The entire foundation consists of 18 board piles split into 3 pile groups for efficient load distribution. Looking at the technical specification, a 12 mm steel casing was used for bore height stability, combined with 15T32 longitudinal bars and 16T16 helical link for reinforcement. Finally, grade 40 or 20 concrete with a 125 to 175 mm slant was chosen to guarantee the bridge durability under heavy traffic and structural loading.
Now, let's look at case study 2, the upgrading of Federal Road FT003 and its intersection in Ratau Panjang, Kelantan. For this heavy civil infrastructure project, the requirements were completely different. We had to support a large bridge structure dealing with massive dynamic traffic loads. Therefore, the team utilized a board pile foundation system, which involved drilling deep holes into the ground and casting the concrete right on site. Board pile provide massive vertical load capacity and excellent lateral resistance, making them the ideal engineering choice for bridge that must withstand continuous heavy vehicle movement and harsh environmental conditions. Now, let's look at how effective was the board piling system for the road project. It proved outstandingly effective at handling massive dynamic traffic. Infrastructure in intersection and bridge approach are highly prone to shifting forces from heavy commercial trucks. By anchoring the bridge piers deeply into stable underground strata, this foundation creates an incredibly rigid matrix. This effectively prevents dangerous pavement sinking where the road meets the bridge, drastically lower future maintenance needs and extending the road lifespan. Finally, let's look at the cost for the infrastructure project. Board piling requires a high initial capital investment, largely due to the strict quality assurance testing required by the standard JKR specification. To ensure total structural safety, the project budget funded 4 static load tests, 12 PDA tests, 18 pile integrity tests, and 18 sonic logic tests. While this extensive testing at upfront cost, it is absolutely essential for public infrastructure. It ensures zero defects in the depth concrete shaft, guaranteeing the bridge remains safe and maintenance-free for decades to come.
For this kind of project, there was 2 issues arise, which is borehole collapse in wet soil, where the bridge is built near a river, so the soil is very soft and full of water. When the hole is drilled, the soil can collapse into a hole, which can trap drilling equipment, damage foundation, and delay the work. So to stop the hole from collapsing, the team used steel casing to support top part of hole, which also filled the hole with bentonite or polymer slurry to keep soil stable until concrete was poured. For future project, use a Seri testing machine to check the drilling mark automatically. Also use a cordon test to scan the borehole after drilling, which help engineer find any problem before concrete is poured. For the second issue is reinforcement cage cannot be installed properly, which during installation, this happened because the borehole had collapsed slightly when there was soil at the bottom, or cage was bent, or the wrong size. This caused delay and could affect strength of foundation. The work was stopped to check the problem. As the solution, the borehole was cleaned and reinforcement cage was repaired and replaced if needed. The cage has to be lowered carefully into the correct position before concrete was poured. For the recommendation of this problem, the worker has to check reinforcement cage before lifting and make sure the borehole is clean and have the correct size.
My name is Asha and I will be presenting the comparative analysis and critical evaluation between two deep foundation systems used in different construction projects. The first project is the completed Masjid Indra Sempurna in Kuantan, which uses precast reinforced concrete square-driven piles, while the second project is the ongoing road and junction upgrade in Kelantan, which uses large diameter board piles. First, I will explain the similarities between both projects. Although they use different piling systems, both projects have the same main purpose, which is to transfer the structural load safety to the competent soil and rock layers. Both projects also require similar preliminary activities before piling work begin, such as mobilization of piling equipment, preparation of piling records, pile head treatments, cut-off works, and pile load testing. These activities are important to ensure the pile achieves the required design capacity and quality. In terms of performance, both piling systems are designed to provide stable and durable foundations. They also undergo pile load testing and dynamic pile testing to verify that the installed pile can safely support the design loads. From the cost perspective, both projects include expenses for piling materials, labor, equipment, testing, and quality control. In addition, the piling works in both bills of quantities are measured as provisional quantities, meaning the final cost depends on the actual pile length and the quantities completed on site. Next, I will discuss the differences between the two projects. The first difference is the type of the piling and its purpose. The MOS project uses 200mm x 200mm precast reinforced concrete driven piles to support building columns and the structural loads of a two-story building. In contrast, the road upgrading project uses 1800mm diameter board piles to support bridge piers, abutments, and continuous heavy traffic loads. The second difference is the construction method. For the MOS project, the piles are precast in a factory and then driven into the ground using the hydraulic hammer. If a greater depth is required, additional pile sections are welded together before driving continues. This method is relatively simple, faster to install and requires less in situ concrete work, making it suitable for medium-scale building projects. On the other hand, board piles are constructed by first drilling a large borehole to required depth. Temporary casing may be used to prevent collapse before the reinforcement cage is installed and concrete is poured using the Trimi method. This process requires specialized equipment, skilled workers, and more construction time. However, it is necessary for infrastructure projects because it provides a much load-bearing capacity. In terms of performance, the driven piles used the most are sufficient because the building mainly carries dead loads and moderate live loads. However, the bridge project must withstand much heavier loads, including bridge weight, continuous traffic loading, braking force, wind, and possible flood impacts. Therefore, the larger board piles provide greater strength, better load distribution, and improve long-term durability. Lastly, the cost implication is also different. Precast-driven piles are generally more economical because they use smaller pile sizes, less concrete and reinforcement, simpler equipment, and faster installation. In comparison, board piling requires rotary drilling rigs, temporary casings, large reinforcement cages, more concrete, extensive testing, and longer construction time. Although the initial cost is much higher, it is a necessary investment to ensure the bridge can safely support heavy traffic throughout its service life. Another difference is that driven piles generate higher noise and vibration during installation, while board piles produce much lower noise and vibration, making them more suitable in sensitive environments.